My pleasure to introduce Eli Grigsby from Boston College, and she'll be talking today on the topological expressiveness of neural networks. Thanks, Eli.
Yeah, thank you very much for the invitation to speak. And yes, you're right. Talking online is a little bit awkward, but I'll hopefully get into the swing of it as I go. So what I want to tell you a little bit about is so neural networks are a very widely used tool in machine learning, and they've been somehow the most useful, at least recently, for some really spectacular applications like training machines to beat the Go masters in Go and things like this. I won't be talking about neural networks somehow in general. I will be talking about a very specific kind of neural network and a very specific problem that should hopefully be of interest to the applied topology community. So let me just go ahead and get started by kind of centering us in where neural networks live, which is in machine learning. So let me first start by telling you a little bit about machine learning, just the very basics, in case you haven't heard an intro talk about it yet. So the basic kind of thing that you do in machine learning, or one basic type of thing that you might do, is you might be modeling some kind of situation, and the best way to do the model is by learning some function. And the idea always is that you guess the type of function first, and then the setup is that you learn the parameters of the function. So just given a bunch of labeled data. So let me give you a very basic toy example so that we can all kind of get situated within the ideas of machine learning. So for example, and we'll come back to this toy example later, you might want to learn the coefficients of a polynomial that best fits some randomly sampled noisy data. So here's a very again, it's a toy example. Here's some data. And the idea is that the data is one-dimensional, and this is like the graph of a polynomial. And you're trying to find the best polynomial that fits this data, best in some sense. And so the idea is that so maybe you might guess that you want to use a cubic polynomial. And so what you're learning during the machine learning algorithm, and again, I won't be talking about the learning part so much in this talk, but that obviously is a very crucial part of the story. But basically what you're doing is you're looking in parameter space. So the parameter space is the space of coefficients of this degree 3 polynomial. And you're trying to find the best, the best coefficients A0 through A3 such that you best fit your data. Okay, so that's a very basic toy example of a machine learning type problem. And the kind of real world question that you might try to answer using this type of model is a decision problem. So the idea would be you have some space of some Euclidean space whose points you're thinking of as being the points for some problem. Say each of the points is represents some email based on some data you've collected, and the question that you're trying to answer is this email spam or not? Yes or no? And so then you might model this as you construct a function on your data space, and you have some threshold above which you classify the email as spam, and if it's below that threshold, you classify it as not spam, and then there's this decision boundary. So this slide is just really to introduce this terminology of the decision regions and the decision boundary of a decision problem, which is coming from some machine learning problem, some modeling problem where you're trying to construct a function to answer a decision problem. So this, from my point of view, for the purposes of this talk, this is what a neural network does very well. Specific very simple kind of neural network does very well. So here's a picture of what I might mean. So again, this is this cubic polynomial, and then we have this threshold, and it defines the region above and the region below the threshold, the values above and the value below the threshold. And then that tells you on and I guess the cursor works, that tells you that this red region in the domain is the yes region, the blue region is the no region, and the green is the decision boundary. Okay, so again, this is, again, just these toy examples. But let me move on now to the kind of question that I'm interested in. Okay, so you might now ask, if you're given a family of functions, and again, in the back of our minds, we're thinking this family of functions is neural networks, particular kinds of neural networks. But since I haven't told you what a neural network is yet, let's just think in the back of our mind polynomials, for example. So suppose you have a family of functions, you might ask, can the decision regions of that family have a particular topological property that you've specified in advance for some choice of threshold? So the kinds of topological features you might be interested in, and you guys know this very well, things like boundedness, connectedness, fundamental group, homology groups, the basic kind of stuff that topologists want to know about spaces. And why might those features be important? Well, again, I mean, this is all sort of motivational, but you guys have probably already drunk the Kool-Aid. I mean, these are the features that are sort of unlikely to be affected by the specifics of how you're representing the data, or perhaps by noise. So what I want to point out here, though, is that these decision regions are defined as, at least in the way that I'm describing it, they're defined as sub and super and level sets of functions. And this should remind you somehow of Morse theory. And what's great about Morse theory is that a lot of the topological features can be read off by the Morse function, by the critical points of the Morse function. This is kind of the whole reason that Morse theory, the whole reason why we all study Morse theory.
Sorry, Ellie,
Okay, so,
can I just ask a question? So maybe to have an example in mind, if I were to try to decide how to classify people as being either urban or rural, you would say that maybe the decision boundary in that situation looks like a circle around the city, or something like that.
Yeah, if your data space is your location.
Right. Okay.
But in general, you're choosing some features to
You have to featurize,
into Euclidean space, and that I guess is the most. That's what I mean by data representation, and that is sort of the trickiest piece.
Right.
Yeah.
All right. Cool. Thank you.
Okay, so this is what we're interested in, is topological expressiveness. So everything that I'm talking about today is a joint project with Catherine Lindsey. And I should also say I've had a lot of conversations with Jesse Johnson, and his theorem is sort of the motivator of what Catherine and I kind of have gone on to do. And again, this work is sort of in progress as well, but it's soon to appear. So anyway, I just wanted to write those names prominently. Okay, so the motivating question for me is going to be, how does the choice of neural network architecture constrain the topological expressiveness of the functions that it can express? So again, I haven't told you what a neural network is. I mean, I did say what I mean by topological expressiveness. So it's the topological features of the decision region, the complexity of the topology of the decision region. So I will say more specifically what I mean by neural network architecture in a second, but you've seen neural networks drawn in the news, even if you haven't learned what they are yet. And so you can see what one might mean by architecture. I mean, it looks kind of like a building. But for now, since we have this toy example in mind, let me focus on that so we can understand what we might mean by the architecture constraining the topological features of decision regions. So again, this is really a toy example, but I want to get our heads in it. How does the choice of the degree of a polynomial constrain the topological features of the decision regions? Well, we can see this kind of right away, how it might do that. So if you have a degree 3 polynomial, well, its derivative is degree 2, so it can have at most two critical points, a maximum and a minimum in this case. So there exists a choice of threshold such that it separates that maximum and the minimum. And so for that choice of threshold, the decision regions are interesting topologically. This is just a one-dimensional example, but you can see the yes region and the no region both have two connected components, and one is bounded and one is unbounded. Whereas if you take a degree 1 polynomial, there's just not much you can get. No matter what you do, you're going to have one connected unbounded component for both of the decision regions. And again, we're starting to see how these Morse theory ideas come into play. Okay, so the conclusion here that I want to start off with before I start talking about neural networks for real is that a function's architecture constrains, very naturally can constrain its topological expressiveness. Okay, so now let's kind of get into the meat of what I want to say. So let me tell you a little bit about neural networks as functions. So there are actually, at this point, many different kinds of neural networks out there. There are many things that people can mean when they say neural networks. I'm going to focus on a particular class, and this is just the standard feed-forward neural networks. And I'll describe somewhat in detail what these are. But you'll see that there's not actually that much to it. So when you see one of these pictures in the news, what you should think of is, well, it's a function, and the vertical, these nodes tell you, so the number of these vertical lines of nodes that you see are the layers of the neural network. So you're going sort of from left to right, and the number of nodes is the dimension of the Euclidean spaces that you're mapping through. So you're thinking here of this neural network as being a function from R3 to R, but it's realized as a composition of functions through the different layers. And these layers are often called the hidden layers of the neural network, the ones that aren't the domain or the codomain. Okay, so what I mean by architecture is literally just the dimensions of the spaces that you're mapping through, mapping from, to, and through. Okay, so now let me tell you what these functions between layers are, because it's actually quite geometric, and this is what I like about the theory. So if you have a function connecting adjacent layers, so a two-dimensional layer and a three-dimensional layer, for example, it's really defined geometrically by three co-oriented affine hyperplanes in R2. So here, the 3 is the number of hyperplanes, and the R2 is where the hyperplanes live. And actually, it's a bit more than this. It's these arrows also have lengths, but most of the information in terms of the topology, I think, is really just the co-orientations and the hyperplane arrangement itself. Okay, so now how is the function defined? Well, Okay, the answer is it sort of depends. The idea is that the components of the function are defined by the hyperplanes, and it's a so-called ridge function with respect to the affine hyperplane. So that means that it is each component is its value depends only on the line, the hyperplane parallel to this particular affine hyperplane. That's why it's called a ridge function. So you know, as you move up and down from, say, H1, the value of the function, that first component depends only on what hyperplane you're on. And if you take a slice, it looks like this so-called activation function. So classically, neural networks were sigmoid neural networks, and the idea was that as you got very far to one side, you approach 0, and very far to the other side, you approach 1. So the idea is that each of these nodes is the answer to some sort of sub yes or no question, and really what we're saying is that this hyperplane is like 1/2, like we don't know whether we're yes or no. But as you go as you go far to one side, you're 0. You're probably no, more and more probably no. As you go further to the other side, you're 1. So that's the basic idea of sort of classical neural networks. In practice, actually, these days, somehow very recently, within the past, I'd say 5 to 10 years, the activation function that has gained prominence is the ReLU function. And it's this really sort of stupid function in a way. It's the identity when you're on the one side, and it's just 0 if you're on the wrong side. Here you're sort of noticing that the regions of this hyperplane arrangement can be labeled with binary tuples depending on whether you're on the side with the co-orientation or the side without the co-orientation. So this ReLU function, I don't even know what the history is of how it came about that it started to get used, but it works much better for some reason, and I don't think there's that much theory behind why it does or why it doesn't. And that's a common theme in the subject, that the applications have been so amazing so quickly that the foundations are not there. Many of the foundations are not there, and that's why I really believe this is a great area to start moving into for everybody. Okay, so here's a sort of fundamental theorem. So again, I'm saying I'm going to focus for the rest of the talk on this most popular activation function, which is the ReLU function. And I'm doing that partly because it's the most popular these days, and partly because actually the geometry then just gets really, really cool. And I want to try to tell you about that. So it's a classical theorem, and by classical, I think this is from like 2014 maybe. Aurora, Basu, Mianji, Mukherjee, that the class of ReLU neural networks is precisely the class of continuous piecewise affine linear functions from Rn to this. So it's going to have to be from to the non-negative real numbers because this activation function just maps everything to non-negative things with finitely many convex regions on which the function is linear. And in fact, these convex regions are convex polyhedra, as shouldn't be surprising since everything is defined with respect to affine hyperplanes. Okay, so now that I've...
And Nelly, can I ask a question about that last slide?
Yeah.
So to get more and more complicated functions, you'll have to sort of change the architecture of the neural network.
That's right. Yeah. Yeah, that's right. That's
Thanks.
Absolutely right. Okay, so let me tell you a little bit about architecture and topological expressiveness. So that was a perfect lead-in question, actually, Henry. Okay, so it is actually a classical theorem in the subject, this universal approximation theorem, and I'm listing some groups of people. So originally, this theorem was proved for the sigmoid activation functions by Cybenko, and then a slightly larger class by Hornick, Stinchcombe, and White. For the ReLU, it was proved in that same paper by this group of four, Arora, Basu, Mianji, Mukherjee. And what it says is that a sufficiently complicated neural network can approximate any continuous function to arbitrary accuracy, so L1, on any compact set. And again, since we're talking about ReLU here, we of course mean functions that map into the non-negative reals. So what I'll say about this approximation theorem is that it's, in a certain sense, it's highly non-constructive. The proof, which I haven't really been through, but the proof, well, yeah, there's sort of various ways to understand it. But the way the proof goes is a lot like the oh, and now I've forgotten the name of the classical Stone-Weierstrass. Showing that polynomials of arbitrary degree can approximate any function on a compact set. Yeah, it's this sort of approximation theory argument. You look at function space and you're saying something about the density of the polynomials of a certain degree within this space, but it's not really telling you. Yeah, it's not really telling you. It's not as constructive as you'd like it to be. So let me just introduce a couple of terms here. So typically we refer to the number of layers as the depth of the neural network, and the maximum dimension of the layers as the width of the neural network. So the classical constructions, so there are actually constructions that are pretty geometric, but these classical constructions are typically on wide and shallow neural networks. So very often they are neural networks with just a single hidden layer that's huge. And the idea behind these constructions is that, if you want to get a function that has certain behavior, you kind of you tile your space with a bunch of hyperplanes, and then you construct sort of like bump functions and this kind of thing. So these constructions, though, are, again, they're very inefficient, and they tend to be sort of these wide, shallow constructions. But we've seen in practice, the practitioners will tell you that in practice, deep neural networks work better. Now, it's kind of unclear whether this is because they're actually more expressive, in the sense that let me just kind of back up to say that there's a notion of theoretical expressiveness, which is it actually possible to find parameters for your function such that you approximate some other function? And then there's the practical expressiveness question, which is if you start at a random with random parameters assigned to this architecture, will a machine learning algorithm find that good modeling set of parameters? So it's not even really clear whether deep neural networks are actually more expressive theoretically, or whether it's just for practical reasons. But in general, I think the point that I want to make is that this is somehow one of the big questions in the subject, that the theoretical explanations for why deep neural networks work so well seem to be inadequate. And I don't think that they yet give a concrete idea of what the functions between the layers are doing. Okay, so let me now kind of swerve a little bit. So So I told you that a sufficiently complicated neural network from the point of view of the total degree, the sums of all of the, sorry, not degree, the sums of all the dimensions of all the layers, the total complexity, is a universal approximator. Now let me give you a negative result, which was proved just within the last couple of years. So by Jesse Johnson for arbitrary, well, not arbitrary, but a very wide class of activation functions. And then Hanin and Sellke independently, but with a very similar idea, just for ReLU neural networks. So what they proved is that a width n neural network on an n-dimensional input space domain, data space. So what I'm saying here is that the dimension of the hidden layers never exceeds the dimension of the input. So if you have a width n neural network on an n-dimensional input space, it is not a universal approximator. And what is cool about the way that they proved this is that this follows from a topological result. So what they prove is that the decision boundary of a width n neural network is either empty or unbounded. So the only kinds of functions that they can approximate are functions of this kind. So you never have like a decision region which is like a disk. It's only ever like, has the topology of like a half space. Okay, so this I think is a really cool result. And the idea here is that a width n neural network is insufficiently expressive topologically. That's the way that we should read their theorem. Okay, so I mean, this is kind of what has motivated my joint project with Catherine Lindsey. So, I mean, basically speaking, what we're interested in is how each layer map affects the potential topological features of the decision region. And we're sort of very far from understanding this in general, but I feel like we're trying to lay down some frameworks and foundations. Okay, so before I get started telling you about that, let me just quickly give you an idea of how the Johnson-Hanin-Sellke theorem is proved. So you can see that actually it's very geometric, and it relies a lot on understanding things about hyperplane arrangements. So very classical mathematics. So I'm going to say this is not the original proof. This is just how we're understanding it based on this sort of piecewise linear geometry, and this will kind of set up what we do later as well. So I'm going to give the proof in the case of generic hyperplane arrangements. So you should think of a generic hyperplane arrangement as, well, it's the sort of generic case. It's hyperplane arrangements where any k hyperplanes intersect in an affine linear subspace of dimension n minus k. So if you have, an n-dimensional space and you have m hyperplanes, you want every k of them to intersect in something of codimension k. Okay, so the first lemma, which really follows inductively from some classical work of Zaslavsky, is that n generic hyperplanes in Rn partition the complement into 2 to the n connected components. So before I was kind of labeling the regions of a hyperplane arrangement with binary tuples. So what this is saying is that when you have n hyperplanes, the regions are in one-to-one correspondence with the binary n tuples. That's not in general true when n is when the number of hyperplanes exceeds the dimension of the space. But in this case, you really have these. It looks like a coordinate hyperplane arrangement. That's what you should have in mind. 2 hyperplanes in R2 generically look like an affine transformation on the on the coordinate hyperplanes, the x and y axis. And the same is true in higher dimensions. Okay, so this is kind of the basic starting point. And if you have, so now if you have a generic ReLU neural network of width n, okay, so you can then prove by induction that if you look at the image of the domain, it's going to look like basically a convex n-dimensional polytope plus some lower dimensional stuff. So here's an example of what I mean. So you can prove by induction that as long as the width of the layers doesn't increase, you're going to get this convex polytope and then some possibly lower dimensional stuff. But the point is going to be that if you want to, so we're trying to show that the decision boundary of such a neural network must be either empty or unbounded. So what we're going to be looking at is, we map the domain into the last layer before the output. And what we're going to be looking at is some hyperplane in that Rn, intersecting it with the image of everything so far, and then taking the preimage of that, and that's going to be the decision boundary. And the point here ends up being that that if a hyperplane intersects this type of object at all, then it's going to intersect the lower dimensional stuff, i.e., this Q or the boundary of P. And then we just have to understand that that this lower dimensional stuff, because of the structure of the function, because of the structure of the neural network functions, or because of the definitions of the neural network functions, you just have to prove that the preimage of anything in this lower dimensional part is unbounded. And so then you have it. So if your hyperplane intersects this image at all, then it has to intersect the lower dimensional stuff, and the lower dimensional stuff has unbounded preimage. So then this is going to tell you that the decision boundary is either empty or unbounded. And you should you should think this is really having to. I'm trying to find find something I can show. I mean, if you have like say a two-dimensional object embedded in R3, you can easily cut it so that it intersects the interior but not the boundary. But really, the point is that these kind of convex polyhedra, or these convex polyhedra, you can't intersect the interior without intersecting the boundary. And it's only the interior that has bounded preimage. So, so this is the kind of flavor of the argument there. Okay, so what I want to say now is that in that same paper, Hanin and Sellke proved that if you increase the width by 1, so if you allow yourself to map into at least one higher dimensional space in the hidden layers, then your neural network does again become a universal approximator. So so that's kind of cool. So this particular topological obstruction vanishes as soon as the width is increased. But again, their construction is a very general one, which is really, really nice. But it's not particularly efficient for any given topological feature that you might be interested in. So let me give a quick example here. This is kind of well known, but if you want one of your decision regions to have a single bounded component, it's really easy to do that just by taking a single hidden layer with just one more than the input width. So what you're supposed to be imagining here is that you have these three hyperplanes that are cutting out this triangle-looking thing. If you sort of perform logic, well, there's sort of more to the story than this. But this picture here, by the way, is taken from something called Neural Network Playground, which was created by these two people that I think are at Google, Sean Carter and I think Daniel Smilkoff. But it's really fun to play around with. You can create a neural network with sort of any of a certain number of activation functions. You can play around with these hyperparameters, and you can train it in real time in your browser, and it's just really kind of fun on these various data sets. You see here these various types of data sets that you can try to get. Anyway, the point I'm trying to make here is that if you want a decision region with a single bounded component, in fact, all you need is a single hidden layer of width, one greater than your domain width. But it turns out, actually, with such a simple architecture, so this is one thing that we prove, that with such a simple architecture, you can't get a decision region with more than one bounded connected component. And actually here what we need is a notion of generic, which we talk about. It's surprisingly sort of a subtle notion, more subtle than you might expect. But let me try to sketch the proof here because it's going to lead us into what we're hoping to do sort of more long term. So what I'm trying to show you is, what I'm trying to sketch for you is an argument for why, if you have a neural network with a single hidden layer of dimension one greater than your input dimension, you can't get more than one bounded connected component for a decision region. And this is in the generic case, so you should think of this as sort of with probability 1. So the idea here is, again, it's all just geometry. There's at most one bounded region in the complement of n plus 1 hyperplanes in Rn. So this is something that it's actually true not just for generic hyperplane arrangements, but also for all hyperplane arrangements. But it's easy to prove for generic ones. Okay, so now the idea is that that we can now orient the one skeleton of this locus of nonlinearity. So the point about these ReLU neural networks is that the hyperplanes are precisely defining the regions of the linear regions of the map. So on each of the regions complementary to this hyperplane arrangement, the function is linear. So this hyperplane arrangement is exactly the locus of nonlinearity for this particular this particular simple neural network. And so we can now orient the edges representing the direction of the increase of the function. So if you were to imagine forming the graph of this function, these arrows would tell you, when you're increasing. So over R2, you would see this graph, and really what you would see is these sort of linear two-dimensional polyhedra and embedded in three-dimensional space. And the main point here is that since the function is linear on each region, this oriented graph really carries all of the relevant topological information about the level sets of the function. So now one thing that you can prove in a pretty straightforward way is that any bounded connected component of a decision region contains a bounded subgraph, all of whose adjacent arrows point in or out, depending on whether it's the yes region or the no region. So the idea here, of course, you're really thinking of this as being like a skeleton of a Morse function. This is like a piecewise linear version of a Morse function. Well, let me just, so in this case, that green dot is this maximal subgraph, and here is what's inside that green square is a bounded connected component, and the green square itself is the decision boundary, or part of the decision boundary at least. So the point is, anytime you have you should think if you had a Morse function on R2, and then you had a level set for that Morse function, the sub-level set or the super level set of that Morse function would be bounded if and only if there is an index, either n or 0 critical point in there. So that's what you should be having in mind here. Okay, so another lemma is that every decision boundary intersects a region complementary to the hyperplane arrangement in a single connected component. And this is simply because, again, the functions on each region are linear. And these, so the level sets are really intersections of, locally of hyperplanes with these linear regions. So you can't have a bunch of different connected components. So now, since we just have a single region which is bounded, this subgraph needs to be in the boundary of this region. So if we had two different bounded connected components, we would then get these two different two different components intersecting this single region, and that's a contradiction. So somehow the fact that there's this single bounded connected component is telling us something about the possible decision regions, and it's not really surprising. It's not really surprising.
So, quick question. I mean, the only place you could have a bounded connected component is inside that triangle in this picture.
Exactly.
And then you're saying this triangle can be cut in two by that decision boundary inside that triangle. But, right. But you also have this lemma that the decision region has to intersect this vertex that you have in green, which is sort of like a a index 0, right. Critical point. I see.
Right.
Very cool.
Yeah, and the point is you can't have multiple index 0 critical points on the boundary of this single bounded region, because then you would have two different connected components for the intersection of this level set.
It's a cool connection with the Morse theory perspective.
Yeah, right. Okay, so let me then close by just telling you a little bit more about what we're doing with this sort of Morse theory perspective. So again, this is kind of a part of a bigger project that's in progress with Catherine Lindsey. But so the point is that actually this point of view about hyperplane arrangements can be generalized. So if you have a neural network with multiple layers, each associated to each of the layers, as I said, is a hyperplane arrangement. It's a co-oriented hyperplane arrangement, but it's also a hyperplane arrangement if you forget the co-orientations. And so there's this notion of a bent hyperplane arrangement, which was first written down by Boris Hanin, so it's the same Hanin and another co-author, David Rolnick. So the idea here is that you take each of these hyperplane arrangements and you pull them back to the domain. And then you take the union of those. Now, what I don't think is in the literature yet, or is really appreciated yet, is that actually this is a misnomer unless you're talking about generic bent hyperplane arrangements. So there are very, very simple examples where if you pull back hyperplanes, you get things which are not codimension 1 as you would like them to be, or for which these intersections are somehow not generic, like you'd like, or not transverse in the way that you would like them to be. So so this picture on the left is an example of a bent hyperplane arrangement, but where one of the hyperplanes is actually this whole negative quadrant, quadrant 3. So what we're really interested in, and what they really are thinking about when they think about bent hyperplane arrangements, is the generic case. And so you have to say precisely what you mean by a bent hyperplane arrangement being generic. And it's actually not quite as, it's a little bit more finicky than you might want it to be. But once you get the definition right, then everything that you want to be true is true. Generic bent hyperplane arrangements are dense in parameter space. And the region's complementary, and actually this proposition B is somehow the thing that makes everything go. I mean, obviously proposition A is important too, but because you want, sort of with probability 1, that a generic bent hyperplane arrangement is what you get. But proposition B is what allows you to do all the constructions you'd like to do that we were doing before. So the regions complementary to a bent hyperplane arrangement are convex polyhedra. In fact, a generic, I should have written generic here. I left out generic. So in fact, a generic bent hyperplane arrangement gives the domain the structure of a convex polyhedral complex. So the sort of codimension 0 pieces are these activation regions, these regions that you would color with, or you would encode with binary tuples. And then it's a polyhedral complex because you can look at the faces of each of the convex polyhedra, and they're also convex polyhedra of lower dimension, and you can keep doing that. So there's really a skeleton associated to it: 0 skeleton, 1 skeleton, etc. Did you have a question, Henry?
Yeah, I do. This is typed in from Trevor Karn. So he asks, is there a distinction between a generic bent hyperplane arrangement and a tropical variety?
No, I think these are really the same thing. Although, tropical varieties are, in the case where your parameters are rational numbers, and also your weights always have to be integers, correct? When you're talking about tropical varieties. But yeah, this is very closely related to that. Yes, absolutely.
Thanks.
In fact, yeah, go ahead.
Oh, I have a similar question, but you finish.
Oh, I was going to say that there's a very nice paper that whose authors I'm now blanking on, but I can send out the link to the list. An ICML paper from, I think, 2018. Some guys from Chicago talked about the relationship between tropical geometry and ReLU neural networks. And in fact, I really firmly believe that if somebody that really knew tropical geometry were to come and start studying these things, that with a lot of the theory that's been developed in that area, could probably make some pretty quick progress.
So I have a similar question, which is a generic bent hyperplane arrangement like a pseudo-plane arrangement from a topological representation of an oriented matroid?
Ooh, I don't know, because I don't know what those things are.
I think it's essentially you want the intersections of things to have the right codimension. So you don't have three lines meeting at a point kind of a thing? Or that's not...
I wasn't able to go that far. I mean, so our definition of generic bent generic bent hyperplane arrangement required only that each hyperplane arrangement was generic. So in each of the layers, it's generic. And then each pair of bent hyperplanes intersects transversely. But what we require is that that all of the faces of each bent hyperplane intersect the codimension 1 stratum of each bent hyperplane generically.
So like no meeting at corners?
Yeah, I mean, the difficulty, of course, is that, well, as you see from this example here, you know, one thing that you might like to do is say, okay, if you look at a particular bent hyperplane like this one, can you see my cursor, by the way?
Yes.
Yeah, if you look at this and then you look at this, you know, you might want to ask that the hyperplanes that these, so each sort of piece of a bent hyperplane is a convex polyhedron in an affine hyperplane. But of course, these three meet at a point which is non-generic, and that's going to happen because that's just the way that they're created. So, yeah, I think it's not. I tried to do what I think you're saying, and have all kind of k-fold intersections meet in the right dimension, but I didn't know how to do it in a very efficient way. And this was enough for our purposes.
Thanks. Maybe I'll email you later because I have thoughts.
Yeah. Sounds good. Okay. Okay. So here's our example, and again, you can do the same sort of thing now. So now that you have this proposition that a generic bent hyperplane arrangement gives a convex polyhedral decomposition of your domain, then you can start orienting the one skeleton based on the direction of increase. And again, this is some kind of right. So this last map determines the direction of the arrows, of all the arrows. And by the way, I should note that the orientation on this one skeleton is not complete necessarily. You can have some flat edges. So for example, you see that these edges here have no arrows on them, and that's because this whole region is flat. It's mapped to the same value. Okay, but the point is you're getting some kind of PL version of a Morse function. And in this case, so again, this is a particular example of a width 2 neural network, ReLU neural network on a two-dimensional input. You have no critical points, or what I call critical regions, of index 0 or 2. So this is another way of seeing in this particular case that you have no bounded connected components of your decision boundary. Whereas in this, this sort of simple example where you increase the width by 1, but you have just a single hidden layer, you can get a single critical point of index, I guess, 0. Okay, so again, this is all part of a bigger project to understand how this oriented one skeleton of the locus of nonlinearity can change as more layers are added, and to really understand how the topological features are encoded in this graph via these critical regions. And the reason why one might hope that you can do this is because this really is looking like a PL version of Morse theory. Yeah, for those of you who do know tropical geometry, this is like the one skeleton of a tropical hypersurface for your tropical function, in the case where your coefficients are integers. Okay, so I will go ahead and stop there.
Thank you so much for the fantastic talk. So for everyone in the audience, please go ahead and unmute yourself, and let's give Ellie a round of applause. The applause sort of comes in waves, apparently. So questions for Ellie?
I have another question, which is more spitballing than a concrete question.
One second, let me mute everybody again who's not asking questions. Hold on. Okay, you should be good, Alex. Go ahead.
So the lemma about a width. So you have Rn. You have your first one-layer network that your decision boundary has to be either empty or unbounded. Is that right?
Mm-hmm. Yeah.
But then if you have n+1, suddenly you're sort of a universal approximation. It had the feel of like a radon theorem type thing, where if you have enough points that you cram down into a low enough dimension, or sort of n+1 points, you can suddenly get any sort of shape you want. It seems like it might it feels like some of these results should extend to an arbitrary decision function, like instead of ReLU, sort of anything that's a little bit, if your decision boundaries are not necessarily hyperplanes anymore, as long as they're just continuous enough.
I see. Mm-hmm.
Like I said, this is more spitballing than.
Yeah, I'm not sure, but yeah, that seems really plausible. I mean, I think the way that I think about it is that, I mean, yeah, somehow if you want to get, yeah, I feel like you just have to map into Rn+1 in order to be able to cut off anything that you want to be able to cut. I mean, that's not exactly true because, for example, I don't know. Let me just get a piece of paper. But like you can take a piecewise linear function on R2 that folds the paper in half and folds the paper in half again. So you're only ever mapping to R2, and then you can cut by a single hyperplane and you can get something. Well, if I hadn't cut it so badly, you would have gotten a bounded decision region. But what we're saying is that these ReLU neural networks can't do those kinds of maps. Those very simple kind of piecewise linear maps, which is interesting in and of itself. But somehow if you map your plane in a piecewise linear way into R3 first, you're sort of getting like the graph of a function, and then you cut. Then you have a much richer space of functions to work with.
Other questions?
Yeah, I have a question. So it looks like a big part of the main proof looks at what kinds of decompositions you can get from a particular class of objects, right? So you've got like half spaces, or think of them as hyperplanes. And so one case where this was studied a lot in the early 90s, it was in data structures for half space range counting. So I've got a bunch of points and I want to count how many points are in a given half space, or I want to just check to see, or sometimes I want to report all those points. And all these methods, one class of methods was called shallow cuttings, was looking for nice sets. But all these methods at some point got back to like the bound on what you could do depended on the VC dimension of whatever your objects were, whatever your ranges were. So is it, in this case, it seems like you also have hyperplanes, which as a range space gives you this VC dimension of n+1. Like, is it possible that maybe there's just some more combinatorial description of what the limits of these methods are? I mean, is there other research about looking at VC dimension as kind of the width bound that you need to be a universal quantifier?
Yeah, I don't know. I don't know. I mean, to be honest, I don't know actually of. I don't know of very many people that are thinking about these topological questions. I mean, I know that there are a good number of people that are thinking about the expressiveness of neural networks. Yeah, maybe in terms of this VC dimension, and other notions of expressiveness in terms of the sort of approximation theory. But yeah, I think I don't know enough about the literature on that. Yeah, I don't know enough about the literature on that.
Okay, thanks.
Yeah.
Other questions? Well, thanks everybody for joining, and Ellie, thank you very much for a wonderful talk. Let me